Buenas tardes, bienvenidos a el segundo coloquio del 2022. En esta ocasión tenemos como invitado al doctor Philip Measor y él nos va a hacer una presentación interesante sobre microdispositivos. El título de su presentación es A Scalable Fabrication Method for Innovative Microdevices. Entonces, vamos a tener este coloquio en una presentación en inglés. Las preguntas, pues de preferencia en inglés o se pueden hacer en español y las traducimos para el profesor. Vamos a tener una presentación como de 30 a 40 minutos y entonces comenzamos introduciendo al profesor. Professor Measor, welcome to our seminarium. I'm going to introduce you to the audience, and then you can start your presentation. Dr. Philip Measor is an assistant professor at Whitworth University in the Engineering and Physics department and leads the Microdevices laboratory. His current research involves the design, fabrication, and application of microdevices, devices with functional elements on the 1 to 500 microns scale. Prior to the Whitworth University, he worked in the semiconductor industry at the KLA Corporation. It is the worldwide leader in process control instrumentation as a researcher, scientist, and applications development engineer. Before the industry, Dr. Measor founded a biotechnology company, Liquilium Diagnostic Inc., to develop new virus and cancer diagnostic devices and instruments. He obtained a PhD in electrical engineering at the University of California, Santa Cruz in 2010. He has more than 45 publications and 7 patents in semiconductor process control, microfluidics, and applied optics fields. Please, Professor, you can start with your presentation.
All right. Well, thank you very much for inviting me to talk in your seminar series. Today I'm going to talk about some work in my lab. So let's see if I can share. And thank you for the introduction. So today I'm going to talk about a method or a scalable fabrication method to make microdevices. Like they said, I'm an assistant professor in engineering and physics at Whitworth University. My lab is called the Microdevices lab that you can visit here. So first of all, I wanted to describe what is a microdevise. So I'm defining this as just a device. So there's a specific application for the particular device, as well as the microscale functional elements. So microscale, like in my introduction, I did determine it's on the scale of 1 to 500 microns. And this image depicts an example microdevice, such as microfluidic connections, so microscale fluid channels that you can add additional functionality. And one thing that microdevices are useful for is to automate analysis with microdevices. So this is a public domain video of a droplet maker that's a very common use for microfluidics, for example. However, many, almost all microdevices today that are in use are used and fabricated using the semiconductor manufacturing methods or microsilicon fabrication methods. And they entail very expensive instruments as well as infrastructure. So we all know that a clean room is used very frequently to make micro devices, such as semiconductor chips. And each device uses multiple expensive pieces of equipment to make it, with each of the physics having to be developed to develop these instruments. And to operate each of these instruments requires highly trained personnel, very frequently having PhDs themselves. But when I went back to academia about 4 years ago, I asked the question, could we make devices, micro devices, using 3D printing? So that's the primary question that I'm asking and demonstrating with my research so far. You might be more familiar with this type of 3D printing, which builds up a three-dimensional structure by extruding thermoplastic, through this nozzle and building it up point by point. However, in my lab, I use this type of 3D printing, which is constructed of essentially a vat of resin, so liquid resin, that when exposed to light solidifies, and you can actually just pull the 3D print out of this resin. And to demonstrate this, we built a custom 3D printer, or so-called SLA, or stereolithography printer, that essentially contained or consists of a UVA light source, shines off a digital micromirror device here, and that essentially is just an array of micromirrors that are very small, and that essentially defines each pixel that you want to print, and it's very easily controllable. And just a simple optics to get the sizing, imaging, as well as straight through an optical window, and we build the 3D print on top of this build plate. And so here's an example of how a print could be constructed. So you simply put a droplet of the liquid resin on this optical window, for example, lower the build plate into this resin, and then pattern it using that light, and it solidifies in that region that is exposed. And then you can simply lift out your print to get your final product. You can, of course, do this multiple times and therefore build up a three-dimensional structure by layer by just lowering it in and making sure it's a very precise distance away from that optical window. And the advantage here is that you can print the entire layer simultaneously, as opposed to that point-by-point fabrication method like that FDM or that nozzle thermoplastic-based method, or some other more popular methods today, such as two-photon absorption 3D printing, that have to be defined point by point. The advantage of that is that it can be much faster to print. So that's the basis of a lot of this technology I'm going to talk about here. And I wanted to share a few demonstrations of different micro devices that we've looked into recently. And the first of which is a microfluidics platform. The second, I'll describe an integrated photonics device, and then finally a biosensor. So the microfluidics device, we were interested in exploring and researching this, this worm, this nematode, that is on the scale of 50 microns in diameter, and they can grow as long as 1 millimeter long. So they're fairly small, and they are frequently looked at in genetic studies, in particular to understand how certain deformations in genetic makeup can kind of deform, say, the organs of a worm, and ultimately can help us understand some origins of certain cancers. The genome of the worm coincides with certain segments of the human genome. Thus, we think we can learn some things from this model organism. It can also be used in pharmaceuticals to develop certain drugs to see how effective the drugs are, for example. So there's some uses there. So first, before we looked at making a device to analyze the C. elegans, we had to make sure that the resin itself would not kill the C. elegans worms. And so we did a biocompatibility study. So that is shown here on the graph, where we looked at the number of worms over a period of 14 days, this being the typical sort of lifespan of a worm. And we started with about 200 worms, and we performed 4 trials of this investigation. And we looked at the population of the worms with the resin, exposed to the resin, and without resin, as we can see here. So the control is the no resin point in gray here. And we didn't see there was a significant difference in terms of the population amount compared to the control. In fact, we saw that the resin actually suggested it was more amenable for the worm population systematically. So we had a higher population of the worms after 2 weeks. So that was somewhat interesting. But nonetheless, it was pretty clear that the resin itself did not accelerate the death of the worms, and so we could conclude that it was indeed biocompatible. So next, we looked at making a microdevice. So we started with a very simple microfluidic device of just a straight channel, one inlet and one outlet. Here's the film of that 3D print that we took off the glass slide that you can see. And if you look at it in under a microscope, as particularly at the channel, this is what you can see. So the channel portion here is in the middle. It's about 150 microns in this particular example. And we can see the print defined on the edges. And this is on the edge of the inlet on the left. So we first started to see if at least we could make channels that are entirely enclosed that could contain these worms. So we looked at these glass microspheres that were approximately 100 microns in diameter and introduced them into the channel. And this is what we saw for one particular experiment. So the glass microspheres can move around freely while in the liquid here. And this suggested that the C. elegans would indeed fit and could be observable. We could still see the shape of the spheres. So this seemed like it would work. And indeed, when we introduced the worms into our 3D printed microfluidic channels, we could indeed see the worms. They were able to be moving around freely within the channel. And so we thought this could be an amenable solution for analysis of these worms. The nice thing here was, so if we just freeze on one of the frames, the interesting thing was this microfluidic channel was entirely enclosed. So that means the top layer had a thin film that was 3D printed, yet we could still see fairly good detail on the worms. So the amount of disturbance optically was fairly low comparatively. So that was somewhat surprising to me. So you can still see the organs, individual organs here in the worm, particularly in the upper left portion. You can see these more oval spheres that are the mouth region of the worm. So you can imagine doing some kind of genetic alteration of the genome of the worm and then seeing how the organs change. This would be one potential example experiment. We also looked at GFP genetically modified worms that were modified to fluoresce in only the mouth region. And so you can see that here with one particular worm, where the mouth region you can see glowing. What this demonstrated was that indeed our microfluidic environment did not interfere optically with this collection of the fluorescence, especially through the 3D printed top layer. And then the device itself, the material itself, didn't have a significant amount of autofluorescence, which is typically one thing we worry about, particularly for biosensors. One thing I forgot to note here is that the typical amount of time to look at these worms and analyze them for the biologists, they had to do this manually under a microscope and look at it. And it typically took them maybe about a week to analyze several hundred worms to do some data collection that was more statistically relevant. Where this device, we could do the same amount of analysis in about 1 hour. So we were able to save the time. Instead of 1 week, we could do this in 1 hour. So that's an improvement in terms of the engineering side. So that was significant. We demonstrated a device that could be used to analyze C. elegans that was entirely 3D printed. Next, I wanted to discuss integrated photonics. So we all know that integrated electronic circuits, or what's called ICs today, are used in all of our electronics, so phones and computers, for example. But there's this whole other realm that's seen as the next generation technology, in particular for quantum computing, called integrated photonics or integrated photonic circuits that has the potential to be kind of a next generation computing platform. And one example of or the basic component in integrated photonics is the waveguide. And one waveguide that we might be more familiar with is the optical fiber waveguide that you can basically guide the light through this fiber, and it becomes a sort of pipe for the light. And you can see the light coming out at the ends here. However, there are a lot of different types of integrated waveguides, or waveguides that could be integrated, that the different structures are depicted here. And the one that we investigated was the ridge waveguide. And so this is just different from the fiber in that it's all done on one plane. So these are another form of planar waveguides. So the ridge waveguide basically consists of a material that looks like this. So in the cross section here on the left, the main thing is that you have a ridge here that's patterned on top of another material of a different refractive index, N2. And it's surrounded by a certain material, this Na with a refractive index of Na. And the condition to get light to guide in this waveguide is that the refractive index of N1 needs to be greater than both of these other refractive indices. And so this allows confinement in the horizontal direction here as well as the vertical direction here. Now, if we look on the side view cross section in the vertical here and in the axial, so the direction that we want light to propagate, the Z direction, this is kind of the structure that we would see for a ridge waveguide. And if you shine light into it, it would reflect and be entirely confined in here, given that it satisfies the condition for certain angles of these rays. Now, this suggests that it's highly sensitive to being able to know what the refractive index is. So N1 in particular. So if we wanted to 3D print this, we had to start with actually understanding and measuring the refractive index of the resins that we wanted to use. However, there was no one that actually investigated these resins, so we ended up doing that in my lab, and we built a custom setup to characterize this using critical angle the critical angle determination method with a pulse refractometer. And we reported those results last year in Optical Materials Express. So we measured a few commonly used 3D printing resins that are available, including Formlabs Clear and Monoprice Clear. But we also investigated our custom resin that was formerly biocompatible using a polyethylene glycol diacrylate base for that. So that's this PEGDA reference. We also we were the first to measure it both polarizations, so TE and TM. So now that we know what the refractive index is, I could design an experiment to build these ridge waveguides, and we went ahead and printed them. So we did a various ranges of waveguide widths that we can see here, range from about 13 microns up to 30 microns. And the thickness of each of these waveguides ranged from about 3.6 to 6 microns. So that's the cross section. If you look at it top down, you could see the waveguides here. You can definitely tell that there's some morphology changes on top of that, some topology. So it suggests that there would be some loss. However, the first question was whether or not we could actually fabricate it and whether it would guide light. So we, just to depict this, so normally without a waveguide, when you switch on the light, it just diverges after it comes out of the fiber optic cable here on the left, and then would go all over the place, and you couldn't really control what would happen to that light. However, if we align that to one of these ridges here, and we could see that it guided the light quite well for several millimeters long. So this was a fairly good demonstration of that fact. We could also see, if we cross-sectioned it and looked at the output of the waveguide, we could see that it was well confined within that waveguide structure. And this showed that it was indeed a multi-mode waveguide, as we would expect for the sizes and the wavelength. And here, maybe at approximately about 5, the 5th order mode that was excited within this waveguide. So this was confirmed that it actually would guide light, and it would confine it within that structure, and it wouldn't leak out of that particular 3D printed structure. Now, that's only one part of it. Is we also wanted to characterize, well, how good was this waveguide? And to do that, we measured the optical power that we excited it with, and the amount of power that we got out of the waveguide after it propagated through. And we looked at the different loss mechanisms. Indeed, it first depends on, well, how much light do you initially get in the waveguide? This kappa value is called the coupling coefficient, as well as the amount of light that's lost as it's propagating through the waveguide, or the so-called alpha or loss coefficient. And if you look at those mechanisms, the model that's consistent, if you want to look at the transmittance, or T, the amount of light, the ratio of the light power out over the power in, is just an exponential decay type solution. And so this gives us a characteristic loss equation that we could explore and measure. And so this is why, so the coupling coefficient is not as interesting in that it's more structural. So if you change the dimensions of the waveguide, you can change the kappa fairly easily, but the loss coefficient is kind of the limit of what you could actually do. So that is typically the merit, the figure of merit that you look at. So this loss coefficient, and it's measured in per centimeter because it's this exponential decay constant. So now I express that in terms of a linear equation by just taking the natural log of both sides, and you can calculate or look at the log of the transmittance that we can measure, and then fit it to this line to find out those fitting parameters, the kappa and the alpha. So the alpha being the interesting thing here. So if you look at that, let's see, this is the 13 micron waveguide. We could see as we varied the length of the waveguide by several millimeters, we could see that there was indeed an exponential decay in the amount of light that came out. And we fit this, it would suggest that there's a loss of about 1.19 per centimeter and a coupling coefficient of about 0.53. And so I wanted to note as well that we measured 95 waveguides, so there's quite a lot of confirmation of each of these points, and it was fairly consistent. So that actually is a fairly low number, especially for integrated waveguides. So this was a surprising result to me, especially seeing some of those topological variations on the waveguides. We also looked at the 20 micron waveguides, and this loss was even lower at about 0.279 per centimeter. And that's an excellent loss coefficient. The coupling increased as we would expect because we got a larger wider waveguide, so it became easier to couple all that light in. So the nice thing was that loss coefficient went down significantly. We also looked at the 30 micron wide waveguides, and the loss actually somewhat actually increased. So it was kind of suggested that it's not so much the loss coefficient dominated mechanism, but more of a kappa dominated loss mechanism. So if we actually could make waveguides that were longer, we probably could measure this loss, but it was the loss was too low to be measured for these particular waveguides. But we were able to get transmittances about 91% through. So it's very high compared to some other work I've done in the past. So in summary, we were able to 3D print ridge waveguides from 13 microns to 30 microns wide, and we demonstrated loss coefficients of from 0.28 to 1.19 per centimeter. And to give you an example to appreciate that loss coefficient, if you considered 100% efficiency coupling and a 1 centimeter long waveguide, a previous demonstration of a 3D printed waveguide using a different method than we did, they could get a loss coefficient about 3 per centimeter, which, if you use this example, would mean a transmittance of only 5% through that 1 centimeter. However, with our 0.3 per centimeter loss coefficient, we can get 74% of the light out afterwards. So I think it's a performance gain there, and is quite significant because it's a log dependent or exponential dependence. So that's another demonstration of the Microdevices lab. And last, I wanted to cover a very exciting thing to me is the Biosensor demonstration. And in particular for detection of viruses and COVID-19 in particular at the time, we were very interested in looking at it. And as we know, COVID-19 detection, as the pandemic progressed, we primarily relied on, at least in the United States, and I suspect in Mexico as well, on a PCR or polymerase chain reaction type tests or nucleic acid amplification tests. And the PCR type tests use these instruments. These are thermocyclers, and it takes 4 to 6 hours to test a single sample to get a good quantitative result. However, at least here in the United States, the limiting thing is not actually how long it takes to test, but the time to actually get the result, which can vary in the United States from 1 day to 14 days or maybe longer, depending on the hospital infrastructure that's in place, and unfortunately the insurance and things like that. So that may be too late for people, in particular for people that we want to get back to work, and if they're negative. And in particular, to do these tests, they're done in centralized labs. So the reason why it takes that long is you have to actually send the sample to a centralized lab that has to be highly controlled, and they're done by individuals that do these tests. So this is typically the place where a microdevice might actually help. And there was a demonstration in 2005 that used glass microfluidics that had an integrated solution that did PCR on a chip. So that was back in 2005. And they showed that you could reduce the amount of time the test actually takes from 6 hours to 30 minutes. So this gives you a scale of, well, maybe you could get a result within the time frame of visiting, say, a doctor or waiting in the waiting room, for example. But we don't see a lot of these glass microfluidic devices actually out there in the market still, 15 or plus years later. And I think primarily the reason is that you're competing against this, just a piece of plastic. So they do PCR in these plastic PCR tubes, and it's fairly inexpensive. The most expensive parts are actually the enzymes that they use in the test itself. And so I thought maybe if I can reduce the cost to make these microfluidic devices, this could be a competitive technology for doing PCR. So we designed a COVID-19 probes, and we used this particular probe in this demonstration. They're called molecular beacons, or hairpin probes. And it consists of basically this hairpin structure that you have on the ends of the DNA probe, a quencher and a fluorophore. The fluorophore can fluoresce if you excite it. However, if it's located next to a quencher, it'll just take all of that light and you won't see any fluorescence. However, if you raise the temperature and break these few bonds in the hair, in that pin portion, it will unfold, and it can be located quite far away from the quencher. There's a large distance dependence here, so that it would fluoresce again. And you can reverse this process. If you lower the temperature, it will go back into the hairpin formation and you won't get any fluorescence. However, the interesting thing is if you introduce a complementary target, it could be DNA or RNA, to this probe, it will inhibit the reformation of that hairpin structure. And thus, if you get any kind of fluorescence after it, after introducing the target, that would indicate a positive, detection of this very specific, strand, the sequence that matched your probe, and hence we could detect COVID-19. And here's a better depiction of that. So if you raise the temperature here, so you have this hairpin formation, raise the temperature, and until all of them are open, and then introduce the nucleic acid target, it would inhibit a lot of these from going back into this hairpin formation. And so this blue line ends up at a low temperature, having a lot of fluorescence in the end. And so that's typically how these probes work. We ended up verifying that these probes indeed worked as we expected. So we got some fluorescence after we reduced the temperature in this particular demonstration. And we also looked at the range for this particular resin and where it would actually give a low autofluorescence. We want to get a really high signal to noise ratio for this. And so when we excited with UV light, we saw that there was some autofluorescence in the about 535, 540 nanometer range. However, in the 600 plus nanometer range, we had fairly low autofluorescence. And so we decided to design our probes for that region initially. So now we have a probe with a device that would be fairly low in autofluorescence. We designed a microarray device here, just in terms of its design, and looked at 1,166 microwells, each of which had dimensions about 116 by 116 microns, and they were about 20 microns deep that were 3D printed. And then we looked at how these structures would change with temperature. And we varied the temperature from 45 degrees C to 135 degrees C, and saw no morphological changes of the wells. So that indicated it would work well for, say, a PCR device. And PCR typically is done in the 90 degrees C range. So this is kind of in our middle of the tested range. So that seemed to work well. And we simply added this to a confocal microscope system. So here's another image of the microwell. We printed them on just a standard 3x1 glass slide. We pipetted the solution into these microwells, added a cover slip, and then looked at it under a microscope, right? And we excited it using this microscope. The confocal microscope, we scanned it across these, and we could detect how much fluorescence we'd actually see. And so when we did that with a positive target that was specific to COVID-19, we indeed saw a lot of fluorescence. And then we used a negative target, we saw almost no fluorescence at all, as you can see here on the left. This used a concentration of a fairly high concentration of 3.33 micromolar for the probes and the target. And if you looked at a region and analyzed the image here, we could see for the negative target, right, or for the one with the positive target, so this was just a synthetic complementary strand of DNA with the probes, we can get a pretty high signal. But with the negative target, so this was just a random sequence of DNA, plasmid DNA, we got a little bit of non-specific binding and some fluorescence here, and thus introduced a little bit of noise. So if we analyze that, we saw a signal to noise ratio of about 40 in this particular experiment. And this suggested we could detect, so the limited detection would be down to 167 nanomolar. So it's a fairly low concentration, and it indicated that it could be good for PCR type measurements. So this is somewhat of a proof of principle result of a 3D printed microarray device that is already potentially useful for PCR type measurements. And so that's one thing I'm fairly excited about. So in conclusion, we've demonstrated a scalable fabrication method to make microdevices, and we demonstrated 3 different applications in microfluidics and integrated photonics, as well as a biosensor demonstration. And we used a method that normally would require a very expensive clean room type environment to make a device, and instead used a very inexpensive 3D printing technology that I approximate is about 100 times cheaper than, or even more than 100 times cheaper than the counterparts in the semiconductor manufacturing world. Not only was that, it normally would take us a month or maybe months long to make it in our research and development world, but 3D printing, I can make these devices in minutes or even seconds. My exposure time is only 1 second, so I can make that device, all these devices, in 1 second. So that is definitely more than 100 times faster than what we could do using silicon microfabrication methods. So this seems like a pretty scalable and interesting method of fabricating microdevices. So I'd like to thank the contributors. All of this work was done using our undergraduate students that participated, and it was an interdisciplinary effort from the physics side all the way to computer science, biology, and engineering, as well as collaborations with the computer science department and the biology department at Whitworth. I also like to acknowledge funding from Whitworth University as well as PACCAR for this work. Okay, so thank you for listening, and we can take any questions at this point. Thank you.
Thank you so much, Professor, for this interesting presentation on the application of 3D printings on microfluidics, photonics, and biosensors. Now the floor is open for questions from here, from the Zoom, and also from YouTube. Any questions? You can ask either in English or Spanish. Okay, I have a question about the use. You used 3D printers using yeah. Did you test? Have you ever tested using 3D printing to make structures with semiconductors directly? For instance, with titanium dioxide or zinc oxide, in order to use these materials as photocatalysts, for instance? Oh,
yeah, that's kind of a next step. I haven't looked at it just yet, but there's some interesting applications indeed. I saw similar type of work when I was in the semiconductor industry, particularly with kind of extreme UV photoresists. They played with additives within a photoresist. So there's some similarities that we could potentially look at in the 3D printing world. So I haven't looked at it just yet, but I'm interested in doing that. I know there's some research in particular of looking at just glass embedded within 3D printed material. And then what they do is a post-process and then kind of sinter it and fuse the glass to make a glass structure. But I think it's fairly new to look at maybe some other combinations there.
Yeah, because we have a world of opportunities because this kind of technology can produce materials with very irregular forms, increasing the specific surface area to make all kind of superficial reactions like photocatalysis, but we can think in another type of reactions too.
Yeah.
We have some questions here. Juan Pablo Aguayo asked, can this technology can be used to print micro or nanoscale surfaces to get super hydrophobic materials?
Oh, super hydrophobicity. I think there's the potential. I mean, you would have to investigate probably different resins. There is some hydrophilicity of this particular resin that I'm using. But I think in principle, you could use some similar, if you can get a resin that would be patterned, that would normally be hydrophobic, you might be able to do a post-process to make it suit the super hydrophobic. This for my work, I'm focused on the microstructures. So I'm looking at more micro scale surfaces, but in principle, you could use like the 2-photon absorption based 3D printing method, and that you can get in the nanoscale. I think as small as 120 nanometers or so. So that could be an interesting thing to look at.
Okay, we have another question from Carla Gomez. She said, thank you for your interesting talk. What kind of resin did you use for the study in worms? Yeah, you showed that there was biocompatibility, but what kind of resin?
Yeah, so the resin was a polyethylene glycol diacrylate base for the monomer. And then we used a standard ErgoCure 819 photo initiator. And then we added some special, other chemicals that we detail in our talk in Photonics West. But there's some added chemicals to kind of make a good print as well as make it biocompatible. So it wasn't the Formlabs and the commercially available resins that we used in that example.
And actually, polyethylene glycol is quite innocuous, right? It's pretty friendly with organisms. And she also asked, also, did your group have some experience with organs on a chip? I'm not sure what is this. You can see this in the chat.
Oh.
Did your group have some experience with organs on a chip?
Organ on a chip. Oh yes, there's. I'm not doing that type of research yet. Yeah, so there's an entire field of 3D printing where you can print structures that look like an organ, and then understand the microfluidic that sort of take place of the vein, say, that connects the blood flow to the organ and from the organ. That can help you in terms of the science. My group hasn't done that yet, although I had some interest from the biology department going that route.
Okay, thank you. And we have another question from Verena.
Thank you very much, Dr. Philip, for your presentation. I'm interested in the rich waveguides. You mentioned that the transmittance gets lost if the dimension increases. Is there a relation? Is there a relation between the imperfections of the printing results?
Yeah, so actually the coupling increases and then the loss decreased as a result of the increase in the dimension. Yeah, there's a correlation. It's basically the amount that's penetrates the surface. So it's typically with that alpha, the main mechanism is typically with scattered loss as it propagates through. So it depends on how long the tail is on the mode that is exposed to that surface roughness. And so typically with the fundamental mode, you have a higher penetration of that EM wave, standing wave that's defined, that interacts with that roughness, and so you get a higher loss. So that happens if you decrease the dimensions. But if you increase it, you get a higher order mode. The higher order mode solution would have a smaller EM wave that penetrates the surface, and thus there's a lower loss due to scattering because of that.
What would be a limit for this process?
Oh, yeah. I mean, you can get as small as the fundamental mode. So the limit on the smaller scale would be 1 mode in that, and then you would just end up losing a lot of your light because the EM wave would just leak out. And I think the ultimate is sort of those slot waveguides that you can get. On the larger scale, they make pretty large fibers. I guess it would just be how large can you make it? You could in principle kind of collect it if it's even larger. And you would still get fairly low loss. Typically, you don't, if you're just trying to deliver power, then you'll have to play the ratio or the optimization of, how much does it cost to make that structure, and then how much light do you want out? So that's usually the trade-off, not so much the limiting principle of the loss there. Yeah.
Thank you very much.
Thank you, Verena. Any other question? or comment here. Yeah, I have another question about the biosensors. It's pretty interesting. Did you test some real samples with your COVID probe?
Not currently, no. You take a lot of extra work to actually do tests on that in a clinically safe environment. So we just use synthetic DNA targets for that particular demonstration to show that this is possible. And then that would be the next step. We would do measurements on clinical samples.
Yeah, excellent. Yeah, it sounds like the next step. Okay, so any other question or comment for Professor Measor? ¿No? ¿Preguntas? ¿Alguien más? Podemos traducirlas si quieren. Okay, well, thank you so much, Professor Measor, for your very interesting talk. We managed to send you your certificate of participation in this seminar. So if you don't have any other question, we can finish here our colloquium. Entonces, podemos dar por terminado el coloquio del día de hoy. Muchas gracias a todos por asistir. Thank you so much for coming and listen to this talk. And see you soon. Thank you so much, Professor.
Thank you.
Nos vemos. Cuídense. Hasta luego.
Thank you very much.